Hey there, kids. This is covalent bonding, day 3 of covalent bonding. The first topic that we're going to hit today, this is just kind of some various topics that we'll hit pretty quick. Bond length and bond strength. So the principle is that the more bonds between two atoms, the shorter the bond length will be, which kind of makes sense if you think about it. Like a single bond will be a really long bond between two atoms, but a triple bond would be a lot shorter. So that's what bond length is and how it corresponds with single, double, and triple bonds. Bond strength, if you start thinking about it, it makes a little bit more sense that a triple bond between two atoms would be stronger than a single bond between two atoms. So it would take a lot more energy to break a triple bond than it would be a single bond. So that's bond length and bond strength, just real quick. Resonance occurs when you can have a double bond somewhere in a structure, but it can be in more than one location. It doesn't have to be in one specific place. If you look at the examples that I have on the screen of CO3, you see that there is a double bond right here in between carbon and oxygen. Well, why isn't it here or here? Well, just because it's not. It can be in any of these locations. See? Okay, resonance just means that that double bond can be in any location within that structure. Okay, polar covalent molecules and nonpolar covalent molecules. So here's polar, first of all. What is polar? Polar is, in chemistry, it's when you have something with opposite charges. So like the opposite poles of a magnet, okay? The opposite poles of a magnet. But in chemistry, when we're talking about the molecular polarity, what that means is that one side would be real positive and one side would be negative. It would be polar. It would have two opposite charges. The reason that it has those two opposite charges is because there's an unequal sharing of electrons in that structure because of electronegativity. Remember, electronegativity is the attraction that an atom has for electrons in a bond. Well, if one atom has a stronger electron or attraction for electrons, then all the electrons are going to be on that side of the molecule. Okay, there will be an unequal sharing of those electrons. A nonpolar covalent bond, there's equal sharing of electrons between atoms. Okay, they both have similar electronegativities, so the electrons don't prefer one atom over the other. Okay, so they're sharing equally. When we're looking at a molecule, trying to determine if a molecule is polar or not, we have two little rules to follow. So either one of these can be true. If either one of these things are true, then the molecule is going to be polar. So if there are lone electrons on the center atom, the molecule is polar. If there are different types of atoms bonded to the center atom, then the molecule is polar. So let's take this first instance. I'm going to show you water. So there's oxygen, hydrogen, hydrogen, lone pair, lone pair. Real quick, what type of molecule is that? Oh, right there. What type of molecule is that? What's the shape called? It's bent. It's a bent molecule. Bent molecules will have two lone pairs on the center atom and two bonds bonded to the center atom. So this is the first. This is an example of this first first check. First check. There are lone electrons on the center atom. Since there are lone electrons on the center atom, that means this thing is going to be polar. Okay, because there's a lot more negative charge on this end of the molecule than there is on this end of the molecule. Okay, oxygen has a greater electronegativity than hydrogen. So that means the electrons are going to want to be this direction, closer to oxygen, giving this side an overall negative charge, and this side of the molecule an overall positive charge. Okay, so that's the first instance, if there are lone pair electrons on the center atom. So if there are different types of atoms bonded, hang on, CH3Cl. Okay, I had to pick a molecule. The second check is that if there are different types of atoms bonded to the center atom. So if we're going to draw this structure, that's a 3, by the way. It's a really crummy looking 3, so I'll redraw it. There you go. Carbon's in the middle. Chlorine, hydrogen, hydrogen, hydrogen. Okay, we got some lone pairs. There we go. Okay, so in this structure, this is an example of that second check. There are different types of atoms bonded to the center atom. Carbon's the center, and look, there's hydrogen, hydrogen, hydrogen. All three of these are the same, but chlorine's not the same. So there are different atoms bonded to the center atom. Okay, this molecule would be polar. I'll give you an example of one that was, there we go. Carbon, hydrogen, 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 hydrogen. So in this case, that neither one of those would apply. This is a nonpolar molecule. Why? Because there are not lone electrons on that center atom, nor are there different things bonded to the center atom. They're all hydrogens. Okay, so this would be a non-polar molecule as opposed to a polar molecule. These two checks will work every time. Check it. If there are lone pair on the center atom or there are different things bonded to the center atom, it's polar. Otherwise, it's nonpolar. Bond polarity is different than molecular polarity. So when we were looking at water, we said that this end of the molecule is negative, this end is positive because it's polar, right? Okay, well, what we're talking about here with bond polarity is the actual bond between hydrogen and oxygen. This bond can be polar or nonpolar, okay? What we're going to do is we're going to subtract some electronegativity differences. And since I do not have an electronegativity table, I'm going to use my cell phone, okay? I pulled up an electronegativity table here to kind of show you how this works with the differences in electronegativity. So the smaller the difference between electronegativities, the more equally shared the electrons are, the more nonpolar the bond would be. The larger the difference between the electronegativities, the more unequally shared the electrons are, and the more polar the bond is. So I'm going to look specifically at that bond. I need to find the electronegativity for oxygen. So I look on my chart here, and since I can't see, I have to make it really big. 3.5. So oxygen's electronegativity is 3.5. Minus, because it's a difference, so I'm subtracting 3.5 for oxygen minus whatever hydrogen is. So go over here, find hydrogen, make it big because I can't see, 2.1. 2.1. So this is the electronegativity for hydrogen, that's for oxygen. 3.5 minus 2.1 is 1.4. The electronegativity difference is 1.4. So let's look at the next slide and see what that means. Here are the electronegativity differences, and yes, you have to memorize this. You will be okay. Memorizing is fine. So my 1.4 difference right here falls into this middle category right here, 0.31 to 1.7. That means that the bond in between hydrogen and oxygen here is polar. Not only is this whole molecule polar, the bonds are polar also. Okay? They're polar also. So what about if the number is less than 1.4? Well, if the bond difference is, or if the electronegativity difference is 0 to 0.3, then it would be a nonpolar covalent bond. Let's look at fluorine. The F bonded to the F. Okay, and yes, there would be lone pair. There you go. There's the molecules. Beautiful. What do you think the electronegativity difference is here? Fluorine's electronegativity is 4.0. Fluorine's electronegativity is 4.0. 4.0. What's the difference? 0. That means this bond right here is non-polar covalent. Take the words separately. Non-polar. That means the electrons are shared equally. Covalent. Why is it covalent? Non-metal bonded to a non-metal. Non-polar covalent. Take the words apart. All right, so let's look at that last one. Let me erase here. That last one. So magnesium bonded to fluorine. Okay, first of all, you should recognize that that's a metal, that's a non-metal. This is an ionic compound. This does not involve sharing of electrons. It involves a transfer of electrons. Magnesium, 2 valence electrons, fluorine, 7. One goes there. Take on another fluorine. And the other one goes there. Okay, so the formula MgF2, because magnesium's plus 2, fluorine's minus 1. All right. This is a covalent, or I'm sorry, an ionic compound. The bond in between the magnesium and the two fluorines is ionic. Okay, it's very, very strong. Let's look at the electronegativity differences here. Let me turn my phone back on. It went off. So we know that fluorine's electronegativity is 4.0. Let's see what magnesium is. So magnesium, let's find magnesium right here. Can't see it because I'm blind. 1.2. 1.2. So what is 4.0 minus 1.2? Okay, that electronegativity difference right here is greater than 1.7. So that means the bonds that are holding the magnesium and the fluorines together are ionic. They're very, very polar. Okay, they're very strong too. So let me back up real quick. Yes, you have to memorize those. You are going to be okay. You can memorize that 0 to 0.3, nonpolar covalent. 0.31 to 1.7, polar covalent. Greater than 1.7, ionic. Has specifically to do with bond polarity. Okay, so we are going to practice. All right, I'm going to draw some molecules, and we're going to determine are they, is the molecule polar and are the bonds polar. So, first molecule, let's see, NF3. So, nitrogen has 5 valence electrons, plus each fluorine has 7, so that's 21, 26 electrons. Nitrogen's going to go in the middle. I'm going to hook these 3 fluorines. Okay, fluorine, fluorine, fluorine. Give it some lone pairs to complete the octet of those fluorines. Okay, then I'm going to look, see nitrogen does not have an octet. I'll put 2 right here. Then I'm going to count and make sure I didn't do anything stupid. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Bam, yep, 26 electrons. Got them. All right, so this is a correct structure. All right, quick. What's the shape of that molecule? Trigonal pyramidal. Okay, that's the shape of the molecule. Okay, completely unrelated, but I wanted to test you anyway. Okay, so we're going to first do molecule polarity. So make sure we can see over here. Molecule. Okay, so we need to see, is this molecule polar or nonpolar? In order to tell if the molecule is polar or nonpolar, we got to check those 2 items. Are there lone pair electrons on the center atom? Yeah. Okay, we can stop there because this is a polar molecule. Got it? All right, so now we go bond polarity. So there's going to be a nitrogen-fluorine bond. So I need to check the electronegativities. Hang on, turn my phone back on. I really should find an electronegativity table. That would be easier. I know that fluorine is 4.0. See what nitrogen is? Nitrogen. Oh, oh my goodness. Sorry about that. Cancel. Nitrogen. Nitrogen right there, 3.0. So 4.0 minus 3.0. The electronegativity difference is 1. So have you memorized them yet? You should have. 0.31 to 1.7. 1.7 is polar. So these bonds are polar. Polar molecule and polar bonds. Does it always happen that way? No. You can have polar bonds and a nonpolar molecule. Okay? That can happen. It's a thing. All right? So let's erase this one. Let's do another one. You do SO2. SO2. Yeah, there we go. SO2. So sulfur has 6 electrons, 6 valence electrons. So do the oxygens. So that's a total of 12. So 18 total electrons. I'm going to put sulfur in the middle. I'm not feeling good about just a straight bond. So I'm going to go ahead and do OO. Give some lone pair here to oxygens. Okay, you kind of get a feel for it. You're kind of like, I don't see that being a linear molecule. Is that 6, 2, 4, 6? Yep. And then I'm going to put 2 lone pair on this sulfur. It's just how I'm feeling. Then I'm going to count and see if I messed up something. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh! Okay, I messed up something. I didn't mess up anything, actually. So here's what we're going to do. We're going to take off, let's take off a pair here. And we're going to put a bond here. And we're going to count. Okay? Oxygens will still both have octets. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Still too many. Let's try again. Take off right here. And no, it won't do. It won't work. Leave that. We'll take this. And we'll take that. And now it looks like sulfur's got way too many. So now we can redo our structure with, like, let's see if that works. See if it is a linear molecule. 2, 4, 6, 8, 10, 12, 14, 16. Nope, it's not. 18. So what I do, I wanted to kind of show you, even though it looks like it might be a linear molecule, it's not. This molecule is not linear. What happened is, okay, first of all, CNOPS applies. Because sulfur and oxygen can be double bonded. These oxygens have to have an octet. Sulfur has what is called an expanded octet. It's what happens when elements are, it's usually around sulfur or period 3 and beyond, okay, and bigger. They can have an expanded octet. They can, the size is such that they can accommodate more than just the 8 valence electrons. In this case, sulfur's got 2, 4, 6, 8, 10 electrons in its, and it's able to accommodate all of those. It can have an expanded octet. It's usually period 3 or higher. Okay, so don't panic when you get here. Okay, it's a thing. You've done the right thing. All right, period 3 or higher has an expanded octet. So now we've got to check the molecule. Okay, our 2 checks. Is there a lone pair on the center atom? Yeah. So this thing is polar. This molecule is polar. I can stop right there. It's polar. So let's look at bond polarity. Okay, we're going to have the sulfur oxygen bond. So let's check electronegativities. Sulfur's electronegativity is 2.5. Oxygen's is 3.5. So I'm just going to do 3.5 minus 2.5 is 1. So this falls between the 0.31 to 1.7. So this bond is polar. The polar bond. All right, that's a lot. That's a lot for your little brains. But y'all are smart kids. Y'all are supposed to have pretty good developed brains. All right, y'all are the good ones. Okay, so let's try this next one. C2H4. All right, carbon has 4 valence electrons for a total of 8, since there's 2 of them. Hydrogen will contribute 4, because hydrogen has 1 valence electron and there's 4 hydrogens. So this should have a total of 12 electrons. I'm going to bond those 2 carbons together because they can bond to one another. Hydrogens are going to go off on the ends, kind of like that, I think. That looks good. Okay, hydrogens are always terminal. Hydrogens couldn't be bonded to each other. Okay, they always have to be on the end. Each hydrogen has an octet. Okay, carbon doesn't. So I'm going to double bond it. Can I? Yeah, it's a legal move because carbon is part of CNOPS. So this is my little structure here. This looks like a pretty little tetrahedral molecule. So we're going to see if the molecule first is the molecule polar or nonpolar. Well, let's check. Are there lone pair on the center atoms? No. Are there different things bonded to the center atoms? No, there aren't. This molecule is nonpolar. Okay, now we have to check bond polarity. There's only carbon hydrogens. Well, there's carbon-carbon bonds. So carbon-carbon bond is going to be 0. So the carbon-carbon bond is nonpolar. Carbon-hydrogen bond, you need to check that one. Turn my phone back on. Carbon's electronegativity is 2.5. hydrogen's 2.1. So 2.5 minus 2.1. Can you still see that? No, there we go. 2.5 minus 2.1 gives me 0.4. So that is between 0.31 and 1.7. So the carbon-hydrogen bond is polar. It is possible to have some nonpolar, some polar bonds inside there. Okay, the molecule itself is nonpolar. This bond is nonpolar. These bonds are polar. All right? Don't be confused. It's okay. All right, O2. Okay, total of 12 electrons, 2 oxygens. Bond them to each other. Okay. Then we check. Let's go ahead and put some electrons here to give them octets. Let's see. Do they have octets? 2, 4, 6, 8. 2, 4, 6, 8. Huh. Well, okay. That looks like it would work. Let's check and make sure we have 12 electrons. 2, 4, 6, 8, 10, 12. Oh, 14. So here's what I'm going to do. I am going to take these off the outside, and I'm going to make a double bond right here. Okay? Oxygen can double bond. Both oxygens are part of CNOPS. Legal move. So let's check now. 2, 4, 6, 8, 10, 12. Okay, oxygen double bonds here. So let's check the molecule first to see if it's polar. Are there lone pair electrons on the center atom? Okay, there's not a center atom. They're bonded to each other. So there's no center atom. They're equal. So this molecule is going to be nonpolar. Bond polarity. Are you that one already? You're going to subtract the oxygen's electronegativities. The difference is going to be 0. So the bond is going to be nonpolar also. Okay? A lot of things you can tell from our little structure there. Okay? A couple more. There. Oh, you can't see that. I keep drawing outside of my screen. Okay, oxygen, 6 valence electrons, 2 fluorines, 20 electrons total. So let's put oxygen here in the middle. How am I feeling? Yeah, I'm feeling that. There, some lone pair, lone pair, lone pair, lone pair, lone pair. And then let's do that. Let's see how this works. 2, 4, 6, 8, so fluorine's good. 2, 4, 6, 8, oxygen's good. 2, 4, 6, 8, fluorine's good. Check to see if we have 20 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There we go. Check. 20 electrons. All right. Is the molecule, oh, what kind of structure is that? What shape? Bent. Check molecular polarity. Okay. Are there lone pair on the center atom? Why, yes, there are lone pair on the center atom. This molecule is polar. Okay, how about bond polarity? Okay, this is going to be an oxygen fluorine bond. So fluorine's electronegativity is 4.0. Oxygen's electronegativity 3.5. It keeps telling me to log in. 3.5. So the electronegativity difference here, since you can't see, is right there. 0.5. 0.5. Which means this bond is what? It's polar. What do you think? Yeah, pretty easy. Getting easier and easier, isn't it? Okay, one more. Remember that means that you're going to add 2 extra electrons in this structure. Okay, sulfur has 6 valence electrons. Oxygen has 6, and there's 3 of them. Now we have to add the 2 electrons in there. So that's 26 electrons. I'm going to put sulfur in the middle. I'm going to go oxygen, oxygen, oxygen. We're going to see how this works out. Might need to change my bond angles. Give oxygen an octet. And I'm giving sulfur an octet. Now we're going to count electrons because everything's got an octet. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So that's the way the structure is? Yup. So if I've got my lone pair there, that means this is a trigonal pyramidal molecule. This lone pair takes up a lot of space, so it's going to move those oxygens, the bonds on the oxygens, away. Okay, so it would be like that. This lone pair would take up a huge space. Right? Oh, look, it looks like a smiley face, but it's not a smiley face. Okay, so that's the structure, trigonal pyramidal. Now we're going to check to see if this molecule is polar. Okay, it's either are there lone pair on the center atom, or are there different things bonded to the center atom? Well, clearly there are not different things bonded to the center atom. They're all oxygens. So are there lone pair on the center atom? Yep. So this molecule is polar. Okay, bond polarity. So we got sulfur here, sulfur and oxygen polarity. Check my table. Sulfur's electronegativity is 2.5, oxygen's 3.5. So yes. So 3.5 minus 2.5 is going to give me a 1. So the bonds here, these bonds, are polar. Okay. I hope you enjoyed that. I like drawing structures. I love covalent bonding. I like this unit. It's kind of fun. Makes everything make sense. So good luck, and we'll see you for day 4.